All right, we are recording. Welcome to class 19 of our Paideia MUMPS, and I don't know how excited you are that the class is going to be soon over, but I'm very excited. So, um, we the matter what that we're gonna the subject matter that we're covering in this class and the next class is essentially advanced mumps and being advanced mumps. uh, One thing you'll notice is that what I'm gonna teach you is stuff that you rarely use, and if even if you write mumps code day to day, you're not gonna use it that often. And essentially what I would recommend that anything I'm teaching you today and the next class is essentially stuff that you're gonna have to look up in the either the GTM or cache reference when you're ready to use it, because it's there there are a lot of sort of either vendor dependent stuff, or the stuff is just way too hard to understand. And I speak of error processing. So we're gonna start off with the job command, and that's pretty easy to understand actually. So I wrote a simple routine called kband job, and I just want us to read it and just understand it. It's not that hard to understand. And let me know. Go ahead and type in the chat if you have any questions while I'm explaining this. So the very first the first line that does something here is I'm locking a node, and the else here is if the lock doesn't succeed, and say I just quit, so I can't so nobody could actually wait for me, they just have to quit. The next line is that there's a global node that controls the stopping, and I just make sure it's killed. And the next few lines is actually where the magic happens. And essentially, you know, I start um, I start with I set the global variable for count to equal uh, either the count itself if it doesn't exist already, or the variable 0, and I add 1 to it. And then I write to the screen the count is equal to the following. And then I pause for 2 seconds, and then I loop and do it again and again and again until I get the signal to stop. And then I unlock it. So that's pretty much it. Anybody has any questions about how this works? All right. So what we're gonna do now is we're actually just gonna run this. We're using a do command, not a job command. So we're gonna do upcaret kband job, and we're gonna see how it works. So there should be nothing surprising here. Now I'm going to switch over to the other screen. So I want you guys to press Control A, Control A. So the other screen is still getting updated. Now I want to stop it. So I'm going to set kband job sub stop equal to 1. And that should stop it. If I switch back, you could see that it's done now. All right. Let me print the routine again so that you can look at it and understand why it stopped. The stop is actually inside of the stop is actually inside of the for loop as a quit condition. Okay, so far so good. All right, so this is great. So what I'm going to do now is that instead of using the do command to run it, I'm going to use the job command to run it. All right. What's the first impression? What's the first impression of what just has happened? Is this even running? Let's find out. The global is this. Let's write it again. Look at that. It's actually increasing. So it is running in the background, but we don't see it. If we do an up Z system, one of these is our job one, but it doesn't. Oh, here it is. If you see process 19394, the last one, that's the one, and it's running in the background, and that's why when you look on the device column, the device column is actually empty. The actual device actually, according to we're running on GTM, and if we do not specify a device for the job in GTM, it defaults to the null device. So that's where it's really going. Let's see where it's up to. Still going. So now we can set our stop node so that it will stop. All right. Let's see whether it's going to increase anymore. That's it. It's done. And let's see if it's there. It's not there anymore. It's gone. So that's it. It's actually not running anymore. All right. One more look at the routine. So you might be wondering, what is this useful for? Why would we ever want to run something in the background? Anybody wants to take a guess? Okay, Tom says report. Linda says if we don't want the user to see it. Actually, we have ways to make stuff that we don't want the user not to see it. So we don't usually use jobs for that. But Tom is right. We do use them for reports. All right, Manohar actually got us the golden answer. One of the biggest primary reasons is for services. So, for example, Vista has a mail server, and Vista has well, essentially, let's just talk about the mail server. Vista has a mail server and it has other services, but the mail server is the easiest to understand. So the mail server has to be continuously running in the background so that it actually, when it actually does receive a message, either from the user on a system to send it outside or from outside to send it back to a user in the system, that it will be able to find it. So that's one primary use, and of course the mail one is just one of many services that Vista has. Vista also has a service to process HL7, and it also has a service to process print jobs. And the other thing which Tom was pretty close to and is reports is that essentially anything that's going to take a long time that the user would do, we do not process in the foreground and have the user see it processing. And so some reports take a very long time to execute, or some jobs would take very long to execute, and because of that, what we do is that we have mumps do it in the background, and so that way the user does not have to wait for it until it's done, because usually the users do want to go home after after a few hours. All right. Well, that's essentially what we use the job command for. I have bad news for you. You're not allowed to use the job command in Vista. Who wants to tell me why? Guesses? No, that's not the reason. It doesn't consume memory. Everything consumes memory. Are you typing something, Linda? Oh, okay. No. Okay. All right. See, Tony is gonna give it a go. And Tom, that's very good. That's very good. That's much closer to the real answer. Although it's not, and Tony is reserved for the kernel. Again, you're getting you. We have to combine your answers to get closer to the truth. Um, the problem with the job command is that the system does not, any mump system does not have an unlimited capacity for executing background jobs. And therefore, what we have to do is that we have to have a job manager in the background that will help us actually uh, actually manage the jobs that the system could perform at the same time. And not only that, that job manager also has capabilities to throttle jobs based on how many concurrent jobs of a specific type could there be at once. That job manager in Vista is called the task manager, and it's the central thing. It's part of the kernel, and it's the central thing that is responsible for um, managing jobs on the system. So the rule is, whenever you want to start a job for Vista, start any job on Vista, you do it through the task manager. You do not do it manually using the job command. Oh, okay. Thank you. So, uh, uh, I have a very distinguished listener, and the distinguished listener is the person who actually wrote Taskman, and he's telling me that the job command is also not portable. It's the parameters for it are not portable, and so another reason to have Taskman is essentially because we want we want to be able to have portable code, and if we wrote that job command inside our code, we would not be able to move it from one mumps implementation to another. So thank you. So in the end, what's let's see, I'm trying to think. What should you take? Oh, go ahead, Tony, you're typing something. Oh, okay, never mind. So um, let's see, what should you take from our little excursion in the job command? Well, I want you to know that it exists and that it creates a new mumps process that does stuff. that essentially lets you do things in the background. I'm going to give you one more example as a sort of go home message, so that we know we could see a real job command in action. And then we're going to move on to our next topic, which is going to be error processing. So what I'm going to show you is this. This is a MUMPS web server, and it uses the job command to create processes every single time somebody connects from on the outside. And I'm going to show you how that works. So I want you to notice that there's a job command to start it that starts it in the background, but that's not the important part for us. That's essentially the same as a do command, and it doesn't help us. But I'll show you the cute part. We're going to look at the cache code because it's easier to understand. So this is the cache code from here to here. And essentially, cache waits until it reads something, and then it creates a child process, which is over here. Let me highlight that. It creates a child process, and that child process is responsible for the rest of the operation. And then once it's done, it goes back to the loop here, goes back to the loop using a goto, and looks for a stop. Essentially, this is a much more complicated version of the code that I wrote for you. It's always the same idea with the job when you're doing something with the job command, that it keeps listening in a loop until you tell it to quit. So that's in essence, a practical implementation of the job command. Well, goto is forbidden in a lot of places, but when when I run out of excuses and my code looks too complex, sometimes I just want to be able to read it, and goto does make the code readable as long as you only have one of it. Okay. All right, and here we go. Thank you, Rick. Rick says deep infrastructure uses goto. That's right. There we are. So, let's move on, and now we are going to discuss the most dreaded topic for me, which is error processing in MUMPS. I'll tell you why it's most dreaded for me, and the reason is very simple. It took me a long time to actually understand it, and it's pretty hard to understand, and I'm going to try to illustrate it as much as I can. So let's talk about the variables that handle error processing in MUMPS. And by the way, for anybody who comes from other programming languages, MUMPS does not have a try catch. You have to simulate it if you want to do it. All right, let's talk about our error trapping variables. And we're going to do a very simple example to illustrate how we use error trapping. So the first one we're going to talk about is $ztrap. It's old, non-standard, and don't use it. That's all I'm going to say about it. So instead, what should you use? Now these are actually new because they were introduced in the MUMPS 95 standard. So you have etrap, which is code to invoke upon an error. Just a moment, guys. Oh, Jignesh sent me an SMS message? That's a bit weird. All right. Let's see. Let me just tell him, Jignesh, try pressing Control A. Control A. He showed up. Okay, good. All right. And the next one upon the next one that we're gonna use is error code, which is actual error code when an error happens. Now the next one we need to talk about is $e_stack is number of levels since we knew $e_stack. You must be thinking, what the hell is that? And then we have $stack itself, and I believe $stack of -1. I can't remember actually what $stack all of it has here. But the important ones is that it's you could do stack level, comma, code. That's the error code, and $stack of stack level. All right, let's see. Here we go. Just a moment. What does -1 stand for?
How many levels?
But compared with how many levels at what time?
At the moment that you run it.
At the moment that you run it. Okay. All right, that's good. So that was the only one I wanted to know. So here's all right, this is the place, and the last one, no, not the last one, but code actual error, actual code causing the error. And the last one here is $stack of -1, which is current stack level. Okay, now what is $st by itself?
Well, don't forget these ones. How did the level start?
Oh.
Very important.
Okay, sure. There's more. And okay, so and we're gonna and $stack. I've actually never known that. A $stack of stack level is how did the level start? Do, job, or extrinsic? Okay. Very good. Now what about $st? Now $st itself is different from st -1. And what does? But what's the difference between that and -1?
Much alike.
Eh?
They're much alike.
No, I thought -1 was different when you're in error processing mode. -1 has something like the deepest level of the error or something like that. Okay, we'll leave this out to the jury, but for now we're gonna say that $st is almost the same as $st stack of -1. Okay, tons and tons and tons of error trapping variables. Most of your life, by the way, and this is what I'm going to cover, and maybe we could cover the rest next week. Most of your life you are going to be reading the VISTA error trap, and that's what we're gonna try to work on, and then we can try simulating our own errors. So let's see about how we could create how we could look at the VISTA error trap. So to look at the VISTA error trap, you type do xter, and here it tells you there are no errors. So we're gonna do, if you do 2 question marks, it tells you, oh, okay, here the errors happen these days. And thanks God we don't clean errors on this system, so we actually have some errors to look at. So this is good. So let's take a look. Let's take a look at this error. So this is the VISTA error trap, and it's invoked using do xter. And let's look at an error. So usually you pick an error number. All right, here we go. Oh, we clarified it. Thank you. All right. So dollar, just a little. I'll get back to it. Never mind. So, all right. So let's look at this, and we type L to print it out, and let's look. Let's look. I'm going to start moving my cursor around so that you guys could follow me. Okay. So remember I told you $E code contains the actual error that happened? Well, here are a few characteristics of $E code. $E code is always delimited by 2 commas. And you see that over here. And if $E code starts with a Z, it means that it's vendor specific. So we're gonna hopefully get to see one that's not Z. $E stack tells you that we're on the 8th level, that our error happened on the 8th level of the stack since we last knew $E stack. And if we never knew, that would mean that we started from the top. This is our actual error trap. And this is our stack level when the error trap was invoked. And let's take a look at the actual stack. And you could see this is E code saying if there's an error, what the place was and what the mumps code was. And if we go down the list, you'll notice that E code is empty. When E code is empty, it essentially means that there has been no error at that level of the stack. So that's good. Huh? Oh, okay. All right. All right. Oops. Just a moment. Okay. That's okay. We'll do it later. So, let's see. So over here, this is the important part. You'll notice that every level here somehow invokes the next level. And I don't know what happened. Let's try this again. Oh, these are the variables. Okay. Here. So if we look at this level, for example, you'll notice it said execute if $data of something, that string. So that and you notice that the next part of the level of the stack of 4 starts with an execute, which means that this stack 3 invoked stack 4. And you're going to notice that the M code looks like this. And then we have a do, which is do %XUCI. And $error code is blank, so the error did not happen here. And then the do %XUCI invokes the next level. And our error code is still empty. That's good. Then I see on stack level 6 that we actually have an error. And I don't know what that error is, to be honest. So let's see. This is a GTM error code, and that's pretty cryptic. It happened here. It says do upcart %XUCI.
It's not a do command, it's a D label.
It's a D label. Oh, okay, sorry. Thank you. It's not a do command, it's a D label. So this is D upcart %XUCI. So this is do SAV, which executed without error, and then D. And therefore this says do NY, do...
Label D.
Oh, label D. Okay, I'm trying to figure this out. Okay,
It's a tough one.
it's a tough one. Label D, then new Y, upcart %XUCI, do 2, quit if 0 contains Y, and then go to @PGM, and then quit. Now, notice, I want you to notice as well that this is not the end of the stack. The stack goes even deeper, and we actually have yet another one. But notice that the last level of the stack is actually our error handler. Now, this is hard to understand. I'm going to go back up. This is ERR plus 3 upcart XUP. So I'm going to show you, going to go back up. And if you remember, our error trap was do error upcart XUP. Therefore, when the error happened, what happened is that MUMPS created a new stack level by invoking the do command to do an error on XUP. And that's what this is. But for us to know in the stack that this is not the stack level, is not the place in the stack with the error, we could see that the error, the A code component of $stack is actually empty. So one thing we want to do now is figure out why doesn't this work? What's wrong with this? Why is there an error? So one thing that helps a lot is the very top of the stack. And here it is. You could see it's this is actually, it says here $ZE, although on GTM that's not entirely accurate, but it's essential. This essential, the $ZE essentially tells you what the actual error was. And it says here, error while Z linking force X. And so the question is, what the hell is force X? Well, I bet looking at this program that force X must be the value of PGM. Now, there's an @ sign on here, and therefore it means that whatever variable, whatever PGM will contain is going to be the object of the goto command. So let's look at PGM. We're going to scroll down, and now we're going to get the list of variables that are in the system when we crashed. And let's find PGM. And here you go. Yep. PGM is indeed force X. Now, from this, we can actually start figuring out what the error was. Now, I know... Oh, here we go. Thank you, Rick. So it looks like it's coming out from here. Is that he sets there's a variable here called in the stack inside of this global node upcart %ZOSF rest job that says XUZ equals force X of manager and then do upcart %XUCI. If you know a little bit more about %XUCI, you'll know that this is actually a cache routine and it's not a GTM routine. and we're running on GTM. So essentially, without going into this error too much further, we know that we have we have a percent ZOSF node on GTM that should not be there. It should actually be undefined and it should just say unavailable. Let's just confirm that. Percent ZOSF of REST job should not actually, we should find it in this environment, but it shouldn't really be there. Copy.
That would be possibly why someone commented and put an arrow pointing towards that line.
That's exactly why. That somebody is sitting right here while speaking.
Oh.
Somebody's way of saying, we need to replace this line with something that runs.
All right. So this is apparently somebody has admitted to being the culprit on not fixing this next to me, and he says that we should be fixing this. But essentially, this is something that will work on cache and it's not going to work on GTM. The other bug is that this upcaret %ZOSF node is written by a program called ZTMGR set. And that program should be fixed so that it would not write this node. All right. That's one bug. Let's take a look at another bug. And by the way, guys, this is valuable training. You're going to be doing this a lot.
The rest of your career.
So, by the way, I have not mentioned how you could log an error. So, to log an error, not that you're gonna do so very much. You do upcaret ZTER. No, you don't have to put percent. It's renamed. You could do percent ZTER as well, but ZTER will work. So I can do this actually. It actually just ran it. This wasn't a compilation thing. So if I do XTER, you'll notice that I have an entry in the error trap that's actually completely empty. It was not an error. It was just me saying that an error happened. So again, we're gonna put two question marks. Actually, under date, we're gonna put 2 question marks and try to find an error that we could look at. So we have 2 errors at 1623. And let's find out what this one is. Now, from the very top of from the very beginning of the error, you could see that the error is essentially that the routine file does not exist. So let's figure out what that file is. So if we could we'll pick 2. We're gonna do. Oh, we could figure out what's wrong here. So apparently VP this program ZVEM EMR MG is actually VPE, and what's it doing is that it's trying to invoke a program called %index. %index does not exist anymore. It was renamed to xindex. So that's why this doesn't exist. Nevertheless, now that we've actually solved our issue, let's just figure out how did it get there, and we're going to look at the stack again. All right, this is when you see that you have $E code repeating itself over and over and over again, it means that you're in trouble. essentially means that your error trap is calling itself recursively, and it's not a good thing. Here's our error trap, and the fact that it calls itself somehow it's calling itself recursively, and I'll tell you why that is in a moment, but it's not very obvious from here. And here it tells you $stack has 18 levels. That's pretty deep, actually. So let's take a look. Now, 0 is GTM's direct mode. And we have stack of 1 that says this. stack of 2. So stack of 1 eventually invokes whatever is in stack of 2, and stack of 2 eventually invokes of what's in stack of 3, and stack of 3 invokes that stack in 4, and 4 is easy to read, thanks God. The rest of them are not. 4 just invokes a program called %RSE, and RSE invokes a program called RCE. Oh. And %RCE invokes scan plus 6 upcard %RCE, and then we have something that's ugly that's going on. And you could see essentially that the error, that it keeps going, it keeps going, and so I personally do not exactly remember of what causes this exact condition where GTM starts losing what the stack is, but it has happened to me before. So we actually do not get the reason for recursion, and the reason for recursion is, remember the very first variable I introduced for you, which was ztrap, which I told you not to use. So ztrap interacts with etrap, and what's supposed to happen is that when you have ztrap, it's supposed to null out etrap, and I believe that happened in this case, except that the ztrap itself had an error inside of it. Oops.
I'll take care of your error. Oh, sorry.
That's still.
They got an error inside of VPE, and VPE did not handle it well.
Yeah. All right. Well, enough about this error. Let's look for another one. Oh, we got 265 errors on this day. Let's find out what happened. All right, let's find out. So this is good. This is the program XPD is kids. So we're going to have fun and figure out what kids was doing here. So let's take a look at 260. So one of the interesting things is that the line in which the error occurred seems to be a very weird line, because that's code in the inside of the VISTA error trap. So we're gonna have to look deeper and see what happened. So I'm gonna show you, by the way, another way to browse the stack. If you do up_P, you get a chance to select a device, and one of those devices could be an email device, which I don't think is configured here, and so you could email yourself or somebody else the actual error. Or you could just page it infinitely, which what I'm gonna do, like this. Oh, good thing I paged it infinitely, because this is crazy. Control A, escape. All right. All right. This is not exactly fun, but we're close. We should not be much farther. Here we go. Our normal variables. So exit +3, XPD ID. We don't know what this is. Wow. 7. So VISTA happened to loop around until it I think what happened is that GTM ran out of stack space.
Yes.
That's what probably happened. And we should be noticing a pattern here. So because this goes in an infinite loop, look what happens. Exit +1, exit +2, error +3, exit +1, exit +2, error +3, exit +1, exit +2, error +3. Okay, that does not help us at all. We actually want to know what really happened. What caused this error in the first place? Well, actually, there are two problems here. I need to backspace a bit. We need to know what caused the original error in the first place, but we also need to know why is the error causing the error to be invoked over itself. So, um, what you're learning here now is the important part of MUMPS error handling is that you need to have an error handler for your error handler so that if your error handler doesn't know how to deal with the error, it can actually crash and stop the process. So I don't think I'm inclined to keep scrolling up, so I'm not gonna do that. But one of these has a problem, and that code is this part. And I am not exactly sure what's wrong with it. And since this is oops, since this was the last error, let's take a look at our date again. Since this was the last error that we saw, 265. Uh-oh. I call this the error trap now failed. Oh, let's do it here. Sometimes selecting the latest one in the error trap could be a problem. So let's do 263. Here we go. Expression expected but not found. And let's go through this from the very top. So yep, I see that the error, well, we need to take a look at the actual error trap as well. So the error trap says, down on here, it says do error upcart xpdij. Therefore, let's see if any one of these has the error code set in the stack. This is weird. The error code is not set in the stack.
It should be there.
It should be there. Yeah, I think we should be at level 4. And here it says set IOTM, that's top margin, and IOBM, bottom margin. And I'm not exactly sure why this is failing, but it's possible that IOSL is not defined, which is screen length. And that's a possibility on why that's failing.
Yeah, had to be.
Now, we can try confirming our hunch by doing the following. Here it asks which symbol. So you could actually just type IO and it will print all the stuff called IO. Let's see if we could find IOSL somewhere here. IOSL is defined. So our hypothesis is false. Maybe. All right. Well, I guess that's good enough for us now for covering how to look at the VISTA error trap. Now we're going to actually try to use the error trapping variable themselves. And that's not going to be fun, but we're going to try to do it. All right, so we're going to begin from the top, and so we're gonna type new dollar. Now, I actually need to mention that each stack level can have its own trap. You can do that by newing each trap and setting it to something new. So here we're gonna set $e trap to equal to go to error upcart kban err1. Now, why did I use a go to? Well, for now, let me tell you one of the very few instances where you actually should be using goto in your code is during your error traps. And we're going to discuss why in a moment. Because we're going to compare the goto with a do. So I'm going to make a very simple error. So I'm going to say read, enter a number as a what's the thing on the bottom of a fraction called as a denominator? Enter 0 to cause an error. And we're going to put it in x. I suppose I should new x then. And then, one over, write this 1 over underscore x is colon 1 over x, right? That should cause an error when we put a 0. Sorry. So here's the error handler. So we should put a quit here. Now, of course, I'm being a bit, what's the word? Passive aggressive. I'm telling them to enter 0, then telling them not to enter 0. All right, this is the simplest. This is the simplest one, and we're gonna walk through it line by line. I know. But before I do this, I actually think I'm going to put this. Into a separate. I'm going to put this into a separate label. Read from the user, and I'm going to put a for loop so that we're going to do the read endlessly, and we're gonna see. I'm trying to see when should we quit. 42. Okay, sounds good. Quit if x is 42. Oh, no need to do two spaces here. And then we're gonna write, thank you for guessing the secret of the universe. And now that we have the error handler, we should, I'm trying to think, there's one extra step we need to do. I'm sorry?
You need X inside the subroutine.
Oh yes, that's right. We need X. Okay, so escape D. Here we go. So yes, I knew the X, but we need X outside. Therefore, I'm just gonna new it on the outside. New X. Alrighty. So our objective. Let's just delete this, so that we won't be obsessive compulsive. Our objective is that if the user enters 0, we actually get to ask them again. And so we'll see if anything we could do actually would work and do it. So let's see. We're gonna go ahead and save it. Now we have a bug in VPE, and now you could understand what it means. It sets the z-trap equal to something, and we said z-trap is bad. So what we do to remove it is we could set $e-trap to equal to break, and $z-trap becomes empty. That's just something that GTM does automatically. Cache has a different way where E-trap and Z-trap interact. So let's just, for now, we're just gonna remember set $E-trap to equal to break is what you want most of the time. So we're gonna do a Z break, and I'm gonna put in my magic string to step. Here you go. All right. Is this the right routine? No, it doesn't look like it.
Oh, K-band error 1.
Error 1. Okay. Oops. Z break K-band error 1. All righty. All right. So this is more like it. Okay. All right. All right. Good. Now let's look at our dollar stack. So our current stack level is 2. So if I do $st of $stack, comma, place, I'm going to see this. So let's keep going. And let's figure out what our first dollar stack, where we got called from, and we could change this to mcode to see how we got called. That's good. If we do -2, no mcode, -1, and where we're currently at. So if I do 3, here you go. 1/3 is 0.333. So that works. Z step into, and I should get asked again. That's good. Now let's enter 0. Alrighty. So this is not very visible, but we are at error +1, K-band error 1. Let's look at our stack. Now, if you remember in GTM, we have G show sub S to show us the stack. And we could also write $stack. And it says we are at 2. Somebody explain this to me. Why are we in the second level of the stack? Okay. Wow, that's weird, right? What's going on? Does anybody who want to have a guess? All right, I'm moving on, and we're gonna try to guess it later. So right now, let me print the routine. Right now, we are actually at the error handler. And so when we quit, the big question is, if we look at the stack, oh, sorry, we don't have, do we have this routine?
Not in this environment.
Not in this environment, okay.
Oh,
Zisha,
no percent. No percent. Do a pro stack.
do upcart stack.
You do have it.
Okay, all
There
right,
you go.
okay. This is a routine that essentially walks $stack, and what we have right now is essentially that we are at read +2, and therefore we should end up back down here. So let's see, z step into. Here's the end of the error handling. And oh, it's telling me you cannot enter 0 again. That's weird. I'm back in the error handler. Oh, what happened? Okay, you guys I know are really confused now. We're gonna run this without stepping. Oh, well, I thought without stepping. So 1 is okay. 2, 3, 4, 5, 0. Okay. First thing you get to see, you cannot enter 0, try again. Then it says it again. Why does it say it twice? Let's see the program. Okay. All right, I'm going to give you a hint. That should be able, now we should be able to find out what the problem is. Oh, sorry. Ah. Oh, that's not good. It's also repeating itself. So, wonder why. There's a reason. Error code is still there. So, here's the magic. So I'll clarify the two things that were strange. The first thing is that one level of the stack seemed to have disappeared without any reason. And that is because we're using a goto. So because we're using a goto, we do not add a level on the stack when the error trap gets invoked. And in many cases, that's what we want. In some cases, that's not what we want. But my experience is that we actually tend to need that more often than not to need it. The other thing is that once we actually process our error code, once we process our error, we need to tell MUMPS that we're done with error handling. And the way we do that is we set error code to be empty. Otherwise, every single time, what's gonna happen is what's happening. So let's actually walk through it again. Let's walk through it again. Oh, okay. So, all right. So let's enter 0. And it's going to try to divide 1 by 0 here. And what's happening is it now went into the error handler because that's what we told it to. But it goes down here, writes the error code. It tells you that you cannot enter 0. Then you go here and it quits. Now let's look at our stack. So when it's gonna quit, what's gonna happen is it's quitting from this line because we use the goto. Remember, this is now where it gets really confusing. We use the goto, therefore, when it hits the quit, it's gonna pop a level of the stack. What level of the stack is gonna pop? The highest one. What's the highest level of the stack? It's 2. Therefore, what's the next line that's going to get executed? It's this one. Okay, but it doesn't end there. When it goes to the next line, it's gonna check and see if the error code has a value. If it does, it invokes the error handler. And therefore, what's going to happen is, even though we just go down here, we invoke the error handler again. Let's look at our stack. You'll notice that our stack is 1 level shallower, and the error handler got invoked again. And we're going to hit the quit, and this quit is going to pop us out. And once we quit, we are back to we don't have any stack anymore. Oops. Here. We're at the very bottom. Okay. I'm pretty sure everybody here in the room is giving me the look of what the hell. And I'm gonna tell you, you're going to have that look for a while. I don't think it just needs lots of practice, and unfortunately, you don't get to practice it a lot. And when you do get to practice it, you start regretting the fact that you practiced it, and you stop practicing. So let's fix it. Actually, let's fix our error trap.
That's what's wrong.
So what we have to do is, now that we know that our error code is so and so, what we're gonna have to do is we're gonna set $error code equal to empty. Now what this does is that resets, says that we handled the error. All right, very good. Let's go ahead and Z-link it, and we're going to remove the breaks and just run it normally. Let's do it again. Here you go. It's working now. Let's do 42. Here you go. So it's working now. Now it's behaving as expected. So we learned. So let's see what we just learned. We just learned that that essentially to handle an error you need to say that error code is empty. All right, and that's pretty important. Now let me tell you about the other biggest problem that we have. What if you have an error code in your error handler? All right. I have no idea what this is gonna do. I'm taking a risk here.
I know exactly what this is going to do.
We'll see what's gonna do. All right. I don't exactly know what it's gonna do, but we've just made an error inside the error handler. See, let's see. Let's see if GTM is gonna handle it okay, or if it's gonna crash and fire.
It'll do precisely what it's supposed to. Here we go.
So I'm gonna print it out so that we know what's gonna do. Oh. Okay. Now, Rick, what did it do? Are you on?
Yeah, I'm plugged in. So what it did was it went to the error handler and blew up again. And because $E trap had not been changed, when it blew up again, it went back to the error handler and blew up again. And it did that over and over and over until it filled up the stack deeper than GTM can handle. And then GTM intervened and said, "You obviously can't handle this error, contrary to what you're telling me with $E trap. So I'm just blowing the whole stack and getting you out of here." And all that happened invisibly.
Okay, so that actually happened.
It did.
It didn't look like it to me like it did, but that sounds good.
It's very quiet. It just went in a tight little loop. Also, it is the most efficient code in MUMPS that you can write. It consumed 100% of the CPU while it was doing that.
Well, hold on a moment. If that was the case, we should see this repeating. Oops.
No,
Oh,
you got to put it above it.
yeah, I know exactly. Oh,
Nope.
okay. Yeah, well, let me see if I know how to put something above anything in VPE.
There you go. Write $ST.
Oh, right, dollar.
That'll be fun. Except you're using a goto. Oh, no, even so. Yeah.
Yeah, well, it should work.
Yeah, it'll work. Oh.
Nah, that's what I thought.
1 divided by 0 is 2.
That's $stack. And then $stack of 1.
Dollar stack of 1.
It unzipped the stack instead of causing an error loop.
Yeah.
Why did it do that?
Now, again,
Print the routine again? Oh, you have a goto.
we could change it to a do, but we need to tell the students what happens when we change it to a do. Now, because now it's going to behave differently.
Sure, change it to a do.
Okay, let's change it to a do. But let's finish up with this example. So because here's the important part. There's a lesson in all of this, despite what you guys think.
There are several lessons.
So the lesson here is that whenever you're entering into an error handler in MUMPS, you need to make an emergency error trap.
Yes.
To replay. And now the emergency error trap, you have to be really careful in how you do it, because you actually have to create an emergency error trap and then create the regular error trap back. So here you have to set $ET equal to halt. So basically, if you get another error while processing your error trap, MUMPS should crash and stop.
Give up. Just get out.
Just give up. Just get out.
You're obviously out of control.
And usually the next thing that we do is in handling an error trap from MUMPS, what we typically do is we actually do something like this. Set $error trap equal quit of $e stack. and then you say set dollar error trap. Oh, actually, hold on a moment. Then inside of the error trap, you say set dollar error code equal quote quote comma u1 comma, which is a user defined error.
2 spaces.
2 spaces after what?
Quit.
After the quit. Thank you. That's right. 2 spaces after the quit. And then what that does is that remember we renewed error stack up above here, and what that does is that it essentially what this line does is that it unwinds the stack.
And code, not e-trap.
Huh?
EC, not ET.
Sorry. Thank you. I made another mistake. So this is supposed to be dollar set dollar e code equal to u. So that causes a simulated error for mumps, and it will unwind the stack.
Yes.
Now, this code is extremely complex to write, and you could guess that somebody in VISTA actually wrote a replacement for this. And so the other way you could write this is go to unwind up caret ZU, which does the same thing.
Wally Fort wrote that.
Alrighty. I don't know how much we should belabor this anymore, but I think you're ready to see a fully fledged error handler in VISTA, now that I gave you enough principles to go on. And so the first one I'm going to show you is one that I wrote. And I hope you could see this. If you can't see it, just let me know. All right. So let's find out where this is invoked. So this is invoked via a do. All right. So the very first thing I do is something called emergency trap, which is what I said. What I said is the very first thing you should do. My emergency trap has three components. One is to log in the actual VISTA error trap what happened. Then call h up caret xus clean, which will clean my VISTA process from all the specific process variables. Then I stop. Now, I'm not gonna do that cache code because it's the one that's actually broken anyway, so it doesn't matter. So while I'm from GTM, I call and get the error code from the kernel. So the kernel has a call to get the error code, and I set that into a variable, and then I log the error. And the actual act of logging the error in %ZTER automatically clears $error code, but I believe I still do it anyway. No, I don't actually, so never mind. So I just left it like that. Then I actually do this, and this is a very sneaky error trap used to pop the stack, and I essentially now this is when you're programming in MUMPS and you're doing error handlers, you're gonna have to decide whether you want to pop the stack after you log the error, or pop the stack after you're done with logging the error. So excuse me, before you log the error or after you log the error. Here I do it after I log the error. And trust me, I did not get this because I understood it. I kept playing with it until I got it right. And eventually I actually keep quitting. Here I say quit if eStack is equal to 1. That's the error trap. And then set error code. Let's figure out how this works. This is hard. Let's go down here. So I set the error trap to a string, and then I set the error code to a quit, to you quit, which is a nonsense error code. Doesn't mean anything. So what happens is that it invokes the error trap, and then it hits quit if $error stack is 1. Well, if you remember, I actually knew $error stack at the very top of the routine. Here it is, new error stack. So $error stack started out with being 0. Is it 1 or 0? I think it's 0.
So
Okay. And so what's going to happen is that this error could have happened at a much higher level in the stack. You know, this code invokes a lot of web service handling code. The error could have happened there. So it's every time it hits this, it's gonna pop it. It's gonna say it's gonna execute a quit, and then what's gonna happen when you execute the quit is that the error code is going to lie around. Now remember, from what we just learned, $error code is the one that says whether you're done error handling or not. And since we're not done with error handling, we're going to keep quitting again until the error stack reaches the number 1. And now when the error stack reaches 1, the question is, what level are we at? Well, the level we are at actually happens to be now, if you remember, we were at 0 here. If the error track is 0, therefore we are at. I'm trying to figure this one out. Where would we be? I would think we would be here, but I'm not exactly sure that this is not exactly correct. The code presumes that we're going to end up here, and that's the part I'm not exactly sure how I got right, but I somehow got it right because I tested it a lot. And so once we reach the end of the stack and we go back to the top, what I do is that I clear the error code, I reset the error trap, and I quit with 0 and I indicate here that the quit 0 is to return from the function to say that it didn't succeed. Okay, here's an example of another trap. This one I did not write. This is in the broker handling code. It's also a very good trap. This is Wally's trap. So there should be an error. Here we go. Here is the error trap. And all of this does is that it sends error information to the client. So we're going to walk through it again. Now, remember, as I told you, first thing you need to do, he did second thing, but that's okay. First thing you need to do is you need to set up an emergency trap, and that's what he does over here. Then he gets, from the kernel, he gets the error code, and he gets the last global reference, which is what LGR is. And then he actually has if $error code contains U411. Now, U411 is an user-defined error code, and I bet you that Wally defined that error code somewhere else in this code, because it's not part of MUMPS and it's not part of the implementer standard. Here he logs the error in the VISTA error trap. And then he says that if the error, and let's find out where this is defined. This variable, this variable is the one that comes back from the kernel. And he says if it contains if it contains a read, or if it contains a write, or if it contains system F, means do exit and halt. So basically, this happens when this is when the system disconnects. Now, if anybody actually knows GTM error codes, GTM does not return these error codes. Therefore, this code is actually broken for GTM. This line is for GTM, and if you guys remember from last class, here he is not using incremental locks. So what does that mean? Well, now we have to think about. Remember last time I told you you should never use non-incremental locks, the old way of doing things. And the exception, of course, is for a wizard like the person who wrote this code. And the wizard who wrote this code says, unlock everything else except this one, which is what this line does. Again, here we go. Rick is pointing out to me, deep infrastructure. When you're in deep infrastructure, which is what this code is, you're allowed a lot more liberties of what you could do. And here is the fancy trap that does the unwinding. And same format. Remember, my error trap quit. My error trap just said quit if not error stack. Here he has a quit if not error stack of not dollar quit. And did we ever cover dollar quit, Linda, or not? I don't think so. Well,
It's part of this.
we should cover it maybe next class because we're out of time. But it's so dollar quit says that you're called with if you're called with an extrinsic, it's going to be 1. So we're gonna talk about it next class. And so here he says, keep quitting, keep quitting, keep quitting. Keep quitting, and then after you're done quitting, set $e code equal to the empty string. Now it tells that we're done when we're done with the error handling. Do this routine and go to restart of xwbtcpm. Now, if you know this code, restart is actually contains the main loop, and then to force the entire this error trap to take place, you set e code to equal comma u99 comma. Okay, I guess we need to wrap up our class. Let's see what we have learned about error trapping. It's hard. I'm showing you this code because I'm showing you how hard it is to get something operational. And trust me, nobody could come up with this line of code in a day and a night. Usually you have to work about a week, 2 or 3 weeks to get this one single line of code right, because it's so hard to get it to work. And in general, in anything that has to do with computer science, writing the code to deal with when everything works correctly is extremely easy. Writing the code that handles errors is very, very hard. Okay, that is the end of today's class, and next class we are going to maybe try to wrap up our discussion of error handling, and we're going to cover transactions, MUMPS level transactions, and that will be it. See you next week.